React Native developers, in this lesson, we're going to build a nice circular slider that we can move around with our finger like this. The position blocks at 0 or 100. And in order to build such cool user interaction, we're going to deploy two interesting recipes. First, trigonometry to be able to calculate the position of the cursor that you see here, depending on the position of our finger. And the second recipe is SVG animation to calculate the length of the arc of circle that represents the progress. So two recipes. Let's have a look at the first one. So here we have the Canva coordinate system. That's the coordinate system of React Native. You know it. 0, 0 is the top left corner of the screen. And on the x-axis, we go to positive values from the left to the right. And for the y-axis, from the top to the bottom. That's the React Native Canva coordinate system. And then there is the Cartesian coordinate system, that's the one we used at school, which is similar to the Canva coordinate system, except that the y-axis is inverted here. And then finally, we have the polar coordinate system, which we use to represent so positions using an angle and a radius. So we can represent different positions. So the way we're going to build the cursor moving around is that we have a pan gesture handler. We move our finger around. Let's say this orange circle is our finger. And we're going to get the polar coordinate of our finger. So we have XY position. We can convert to first to a Cartesian coordinate system depending on the center. Here we're going to use the center of the circle. And then so this Cartesian coordinate to polar coordinate. So we have an angle here and a radius, which is the length of this orange arrow here. So we have our polar coordinate system. We change, so it's a radius and an angle. We change the value of the radius to be the radius of the circle. So that gives us the position of the cursor around the circle. And then we convert this new polar coordinate back to the Canva coordinate system. And that will give us the proper translation around the circle. So here, the circle goes from 0 to 2 pi, full revolution. Half of the circle is 1 pi. And some of the functions we're going to use go from 0 to pi and then from -0 to -pi. So we're going to need to normalize the values. So if we have a negative angle value, let's say -half a pi here, we can add 2 pi, so to have a 3/4 of 2 pi. So to have always positive values that go from 0 to 2 pi. This will help us with the interpolation of values. Because if we use values that here, positive values, negative values, it's going to be too complicated to calculate the progress. So how are we going to do these coordinate conversions? We're going to use functions from Redash that do all the job for us, but let's go over the math quickly because it's very simple. So to go to Canva to Cartesian, we just remove the center, x0, xy, to the x and y value, right? Because here we have 0, 0, but the center of the circle is at some position. And then the y-axis is inverted, so we multiply everything by -1. And then we have Cartesian to polar. So the angle we can calculate using trigonometry. So we have here the Wikipedia page for trigonometry. Tangent of alpha is a divided by b. So a here is our y position, right? This one. And b is the x value. So we have tangent of alpha is y divided by x. So alpha is inverse tangent of x divided by y. And here, actually, we're going to use a function called a tan chu of yx, which is the same function, but takes care of edge cases such as division by 0, for instance. And then the radius, we can calculate. So it's a distance from the coordinate to the origin of the Cartesian coordinates. And this one we can easily find using the Pythagore theorem. So we have r square equals r square, r power 2, r square, yeah, equals y square plus x square. So that gives us r is square root of x square plus y square. So here, Cartesian to Canva, we have the opposite formula, and we use also trigonometry to go from polar, so radius, cosinus, to xy axis. And here again, we have the formula given to us by Wikipedia. Two other formulas important to calculate more like the SVG animation. The circle circumference is 2 pi times radius. It's actually, and the arc length is alpha times radius. It's actually the same formula, but the circle circumference, we take the angle, which is 2 pi, the full revolution. But we can have here any angle times radius, which gives us the length of the arc circle. And this we're going to use to do the SVG animation. So how are we going to do? So that's part one. How are we going to do part two, the SVG animation? So we have our circle here. And so here we have a radius of 250. So we can calculate the circumference of the circle. So that would be 250 times pi, let's say 314 times 2, so 2 pi. So we have 1570. So we can have a gap of the circumference. And then we can add a progress value here to draw the circle. So 100% would be 1570. You see here, I can put only like, let's say, half of that, approximately 800. I can put 200. So you see, I can draw progress like this. And so this is the concept we're going to use in SVG to go from 0 to a full revolution. All right, so let's get into the code. So here I'm going to switch to the boilerplate project, and you can do the same in case you want to follow along with this example. So here we have our boilerplate project. So we have the main file is called circular slider. So where we have the circular progress and the cursor. This is the cursor, this is the circular progress. And so the first thing we're going to do is to create a theta value. So theta value is going to be passed to both of these components. The cursor is going to write the value depending on the pan gesture handler. And the SVG component will animate depending also on the theta value. So let's create it. So use shared value. And I have a default position here, which we calculate. So we convert the 0, 0 position using the center of the circle to polar coordinate. That gives us the default theta value. And so we can pass it here as parameter to the cursor. So now we get theta. So what we need to do is to wrap this cursor into a pan gesture handler. And so since this one becomes a children, it needs to be an animated view. And we need our on gesture event, which we create using use animated gesture. So now, depending on the position of the finger, we're going to write theta. So on active, we have event, value, and context. And so what we can do is that we have translation X, translation Y from event. And we can convert this coordinate into polar coordinate. So we want, let me call it alpha. And so we're going to do canva to polar. So X is translation X, Y is translation Y, center we have here, and we get the angle. Now we can convert new coordinate system. Oh, let me simply actually assign theta dot value to this new angle value. Let's see how it looks. So it's not moving because we need to assign also the translation. So I'm going to create a new animated style. So we have style is use animated style. And we're going to return a transform with translate X and translate Y, which we're going to get from the theta value. So we're going to convert theta and radius of the circle to Canva coordinates. So we're going to have X, translate X, Y, translate Y, and we're going to do polar to Canva. Theta is theta dot value and radius is R. And we need to pass the center as parameter. The center of the polar and Cartesian coordinates. This one here, no, this one looks correct. So you see here it moves the cursor nicely around, but what happens now? You see it resets. We need to remember the position across gestures. You know the drill, it's always the same. And we make our gesture stateful using the context, this little object here. So we're going to have on start. So event context. And what I'm going to do, I'm thinking of creating a X and Y animation value to store the translation. Or we store this value here. Let's do this one. So here we have XY. And we can do context.offset X equals X, context.offset Y equals Y. And here, so we have XY, and X is context.offset X plus translation X, and Y is context.offset Y plus translation Y. Syntax error here. But in fact, I could even simplify this by writing offset equals, and here we would have .x .y. So let me reload. So we move around and the position is remembered. It's pretty cool, no? Now we do need to do two things, but maybe, yes. Before we do the SVG animation, we need proper theta value. So here we go from -0 to -pi, and then here from 0 to pi. And if we want to animate the progress in SVG properly, we need to go from 0 to 2pi. So we're going to need to normalize this here. Let me store it into a variable. So if value is positive, no problem, we return value. And if value is negative, we need to add 2pi. So 2pi plus value. And that's going to give us, so let me add a log for you, just so we get a sense of what's going on. So before, we have a value, and after, we have theta.value. So here, okay, let me reload. So here, positive values, they should be the same, and they are. Now, negative value, we have the proper after positive, which goes, you see, from 0, 20, so 2pi. We convert from the negative value to something that goes from 0 to 2pi. So that's perfect. Now we can do the SVG animation because we have really good values for theta. So that's pretty exciting. Let's do, so now, so if we go back here, we can now pass theta to the circular progress to animate it. So we receive theta, and we're going to animate the circle using the technique we've seen on the sketch. So animated circle is animated, create animated component of circle. So we need to create the stroke dash array that is circumference. So we can have a full circumference and an empty circumference. And now we just need to have the stroke offset. I think it's, is it stroke dash offset? Let me check. How is this property? So it's stroke dash offset. Perfect. So let's calculate it. So we're going to have props, use animated props, and we're going to return stroke dash offset. And stroke dash offset is theta dot value times what, guys? Times radius. It's the formula we've seen here. Oops, this one. And that we are using here with the value 2pi. So that looks good. Let's assign it to animated circle. So we have animated props. Isn't that cool? I think it's pretty cool. And I mean, it's pretty like efficient, right? So I find it to be quite a simple and efficient user interaction to build. Pretty straightforward. So here we can do like full revolutions, and in some apps, that's how it is. For instance, the Apple bedtime. But just for fun, let's clamp the value so we cannot go below 0 and we cannot go more to 100. I feel that it's also a pretty common use case. So the way we're going to do this, we're going to look. So we're going to clamp the Y value for particular cases. So Y1 is the non-clamped Y value, but we need to clamp it. So Y. If we are on the left side, we don't need to clamp anything. And we're on the left side if X is below R. Here we have 0, here we have R, here we have 2R in Canva coordinates. So if X is below than R, we don't clamp anything. So we return Y. And now now we need to clamp the Y value, but depending on if we're coming from the bottom or if we're coming from the top. So depending on the theta value, if theta is between 0 and pi, or if theta is more than pi. So if theta dot value is less than pi, we need to clamp from Y value from 0 to R, and if not, from R to 2R. So clamp Y1 to 0R. If not, we clamp from Y1 to R to R. Let me reload. So here you see it's clamping nicely. And here, here from the top, it's not clamping, but I know why. It's because here we have R, so it needs to be a little bit less than R. So it can be 0, for instance, 0, 0, 1. Let's have a look. So here it's clamping from the top, it's clamping from the bottom. Overall, really fun user interaction. How easy it was to do is really, I think, testimony of how great Reanimated 2 is, and how, because we write JavaScript code, it's like so direct. We use Redash to do the trigonometry functions to convert to Polar and Canva and back and forth. But these are also very easy to write in plain JavaScript, where when we had to do it in Reanimated 1 was a bit more work because we have all these animation nodes, and we had to do an implementation of eta and 2, and we had to check that it was matching exactly the same result, same precision than math.hu. Here we can just use math.hu. So pretty also fun SVG animation, pretty straightforward stuff. And again, we added the clamping to not go below 0 or over 100 using plain JavaScript code, less than, greater than clamp. Quite refreshing when coming from Reanimated 1. So in the next lesson, we're gonna, we're now comfortable building such somewhat complex user interaction. Next lesson, we're gonna ramp it up by building a very cool user interaction on a D3 graph. So this is also gonna involve some mathematical tools, SVG animations. So I'm really looking forward to see you in the next lesson.